In this sequence of lectures, we're going to learn asymptotic analysis. This is the language by which every serious computer programmer and computer scientist discusses the high-level performance of computer algorithms. As such, it's a totally crucial topic. In this video, the plan is to segue between the high-level discussion you've already seen in the course introduction and the mathematical formalism, which we're going to start developing in the next video. Before getting into that mathematical formalism, however, I want to make sure that the topic is well motivated, that you have solid intuition for what it's trying to accomplish, and also that you've seen a couple simple, intuitive examples. Let's get started. Asymptotic analysis provides basic vocabulary for discussing the design and analysis of algorithms. And while it is a mathematical concept, it is by no means math for math's sake. You will very frequently hear serious programmers saying that such and such code runs in O of n time, whereas such and such other code runs in O of n squared time. It's important you know what programmers mean when they make statements like that. The reason this vocabulary is so ubiquitous is that it identifies a sweet spot for discussing the high-level performance of algorithms. What I mean by that is it is, on the one hand, coarse enough to suppress all of the details that you want to ignore. Details that depend on the choice of architecture, the choice of programming language, the choice of compiler, and so on. On the other hand, it's sharp enough to be useful, in particular to make predictive comparisons between different high-level algorithmic approaches to solving a common problem. This is going to be especially true for large inputs. And remember, as we discussed, in some sense, large inputs are the interesting ones. Those are the ones for which we need algorithmic ingenuity. For example, asymptotic analysis will allow us to differentiate between better and worse approaches to sorting, better and worse approaches to multiplying two integers, and so on. Now, most serious programmers, if you ask them, what's the deal with asymptotic analysis anyways, they'll tell you, reasonably, that the main point is to suppress both leading constant factors and lower order terms. Now, as we'll see, there's more to asymptotic analysis than just these 7 words here, but long term, 10 years from now, if you only remember 7 words about asymptotic analysis, I'll be reasonably happy if these are the 7 words that you remember. So how do we justify adopting a formalism which essentially by definition suppresses constant factors and lower order terms? Where lower order terms, basically by definition, become increasingly irrelevant as you focus on large inputs, which, as we've argued, are the interesting inputs, the ones where algorithmic ingenuity is important. As far as constant factors, these are going to be highly dependent on the details of the environment, the compiler, the language, and so on. So if we want to ignore those details, it makes sense to have a formalism which doesn't focus unduly on leading constant factors. Here's an example. Remember when we analyzed the merge sort algorithm, we gave an upper bound on its running time that was 6 times n log n plus 6n, where n was the input length, the number of numbers in the input array. So the lower order term here is the 6n. That's growing more slowly than n log n, so we just drop that. And then the leading constant factor is the 6, so we suppress that as well. After those two suppressions, we're left with a much simpler expression, n log n. The terminology would then be to say that the running time of merge sort is big O of n log n. So in other words, when you say that an algorithm's running time is big O of some function, what you mean is that after you've dropped the lower order terms and suppressed the leading constant factor, you're left with the function f of n. Intuitively, that is what big O notation means. So to be clear, I'm certainly not asserting that constant factors never matter when you're designing and analyzing algorithms. Rather, I'm just saying that when you think about high-level algorithmic approaches, when you might want to make a comparison between fundamentally different ways of solving a problem, asymptotic analysis is often the right tool for giving you guidance about which one is going to perform better, especially on reasonably large inputs. Now, once you've committed to a particular algorithmic solution to a problem, of course, you might want to then work harder to improve the leading constant factor, perhaps even to improve the lower order terms. By all means, if the future of your startup depends on how efficiently you implement some particular set of lines of code, have at it. Make it as fast as you can. In the rest of this video, I want to go through 4 very simple examples. In fact, these examples are so simple, if you have any experience with big O notation, you're probably better off just skipping the rest of this video and moving on to the mathematical formalism that we begin in the next video. But if you've never seen it before, I hope these simple examples will get you oriented. So let's begin with a very basic problem, searching an array for a given integer. Let's analyze the straightforward algorithm for this problem, where we just do a linear scan through the array, checking each entry to see if it is the desired integer t. That is, the code just checks each array entry in turn. If it ever finds the integer t, it returns true. If it falls off the end of the array without finding it, it returns false. So what do you think? We haven't formally defined big O notation, but I've given you an intuitive description. What would you say is the running time of this algorithm as a function of the length of the array, capital A? So the answer I'm looking for is C, big O of n. Or equivalently, we would say that the running time of this algorithm is linear in the input length n. Why is that true? Well, let's think about how many operations this piece of code is going to execute. Actually, the lines of code executed is going to depend on the input. It depends on whether or not the target t is contained in the array A, and if so, where in the array A it lies. But in the worst case, this code will do an unsuccessful search. T will not be in the array, and the code will scan through the entire array A and return false. The number of operations then is a constant. There's some initial setup perhaps, and maybe it's an operation to return this final Boolean value. But outside of that constant, which will get suppressed in the big O notation, it does a constant number of operations per entry in the array. And you could argue about what the constant is, if it's 2, 3, 4 operations per entry in the array. But the point is, whatever that constant is, 2, 3, or 4, it gets conveniently suppressed by the big O notation. So as a result, the total number of operations will be linear in n, and so the big O notation will just be O of n. So that was the first example. In the last 3 examples, I want to look at different ways that we could have 2 loops. And in this example, I want to think about one loop followed by another. So 2 loops in sequence. I want to study almost the same problem as the previous one, where now we're just given 2 arrays, capital A and capital B, let's say both of the same length n, and we want to know whether the target t is in either one of them. Again, we'll look at the straightforward algorithm where we just search through A, and if we fail to find t in A, we search through B. If we don't find t in B either, then we have to return false. So the question then is exactly the same as last time, given this new, longer piece of code. What in big O notation is its running time? Well, the question was the same, and in this case, the answer was the same. So this algorithm, just like the last one, has running time big O of n. If we actually count the number of operations, of course, it won't be exactly the same as last time. It'll be roughly twice as many operations as the previous piece of code. That's because we have to search 2 different arrays, each of length n. So whatever work we did before, we now do it twice as many times. Of course, that too, being a constant independent of the input length n, is going to get suppressed once we pass to big O notation. So this, like the previous algorithm, is a linear time algorithm. It has running time big O of n. Let's look at a more interesting example of 2 loops, where rather than processing each loop in sequence, they're going to be nested. In particular, let's look at the problem of searching whether 2 given input arrays, each of length n, contain a common number. The code that we're going to look at for solving this problem is the most straightforward one you can imagine, where we just compare all possibilities. So for each index I into the array A, each index j into the array B, we just see if AI is the same number as BJ. If it is, we return true. If we exhaust all of the possibilities without ever finding equal elements, then we're safe in returning false. The question, of course, is, in terms of big O notation, asymptotic analysis, as a function of the array length n, what is the running time of this piece of code? So this time, the answer has changed. For this piece of code, the running time is not big O of n, but it is big O of n squared. So we might also call this a quadratic time algorithm because the running time is quadratic in the input length n. So this is one of those kinds of algorithms where if you double the input length, then the running time of the algorithm will go up by a factor of 4 rather than by a factor of 2, like in the previous two pieces of code. So why is this? Why does it have quadratic running time, big O of n squared? Well, again, there's some constant setup cost which gets suppressed in the big O notation. Again, for each fixed choice of an entry I into array A and an index j for array B, for each fixed choice of I and j, we only do a constant number of operations. The particular constants are relevant because it gets suppressed in the big O notation. What's different is that there's a total of n squared iterations of this double for loop. In the first example, we only had n iterations of a single for loop. In our second example, because one for loop completed before the second one began, we had only 2n iterations overall. Here, for each of the n iterations of the outer for loop, we do n iterations of the inner for loop. So that gives us the n times n, i.e. n squared total iterations. So that's going to be the running time of this piece of code. Let's wrap up with one final example. It will again be nested for loops, but this time we're going to be looking for duplicates in a single array A, rather than needing to compare two distinct arrays A and B. So here's the piece of code we're going to analyze for solving this problem, for detecting whether or not the input array A has duplicate entries. There's only two small differences relative to the code that we went through on the previous slide when we had two different arrays. The first change won't surprise you at all, which is instead of referencing the array B, I change that B to an A. Right, so I'm just going to compare the ith entry of A with the jth entry of A. The second change is a little bit more subtle, which is I changed the inner for loop so that the index j begins at I plus 1, where I is the current value of the outer for loop's index, rather than starting at the index 1. I could have had it start at the index 1. That would still be correct. But it would be wasteful, and you should think about why. If we started the inner for loop's index at 1, then this code would actually compare each distinct pair of elements of A to each other twice, which of course is silly. You only need to compare two different elements of A to each other once to know whether they're equal or not. So this is the piece of code. The question is the same as it always is. What, in terms of big O notation and the input length n, is the running time of this piece of code? So the answer to this question, same as the last one, big O of n squared. That is, this piece of code is also has quadratic running time. So what I hope was clear was that, whatever the running time of this piece of code is, it's proportional to the number of iterations of this double for loop. Like in all the examples, we do constant work per iteration. We don't care about the constant. It gets suppressed by the big O notation. So all we got to do is figure out how many iterations there are of this double for loop. My claim is that there's roughly n squared over 2 iterations of this double for loop. There's a couple ways to see that. Informally, we discussed how the difference between this code and the previous one is that instead of counting something twice, we're counting it once. So that saves us a factor of 2 in the number of iterations. Of course, this 1/2 factor gets suppressed by the big O notation anyways, so the big O running time doesn't change. A different argument would just say, there's one iteration for every distinct choice of I and j of indices between 1 and n, and a simple counting argument says that there's n choose 2 such choices of distinct I and j, where n choose 2 is the number n times n minus 1 over 2. And again, suppressing lower order terms in the constant factor, we still get a quadratic dependence on the length of the input array A. So that wraps up some of the sort of just simple basic examples. I hope this gets you oriented. You have a strong intuitive sense for what big O notation is trying to accomplish and how it's defined mathematically. Let's now move on to both the mathematical development and some more interesting algorithms. In the following series of videos, we'll give a formal treatment of asymptotic notation, in particular big O notation, as well as work through a number of examples. Big O notation concerns functions defined on the positive integers. We'll call it T of n. We'll pretty much always have the same semantics for T of n. We're going to be concerned about the worst case running time of an algorithm as a function of the input size n. So the question I want to answer for you in the rest of this video is, what does it mean when we say a function T of n is big O of f of n? Where here f of n is some basic function like, for example, n log n. So I'll give you a number of answers, a number of ways of to think about what big O notation really means. But for starters, let's begin with an English definition. What does it mean for a function to be big O of f of n? It means eventually, for all sufficiently large values of n, it's bounded above by a constant multiple of f of n. Let's think about it in a couple other ways. So next I'm going to translate this English definition into a picture, and then I'll translate it into formal mathematics. So pictorially, you could imagine that perhaps we have t of n denoted by this blue function here, and perhaps f of n is denoted by this green function here, which lies below t of n. But when we double f of n, we get a function that eventually crosses t of n and forevermore is larger than it. So in this event, we would say that t of n indeed is big O of f of n. The reason being that for all sufficiently large n, once we go far enough outright on this graph, indeed a constant multiple times f of n, twice f of n, is an upper bound on t of n. So finally, let me give you an actual mathematical definition that you could use to do formal proofs. So how do we say in mathematics that eventually it should be bounded above by a constant multiple of f of n? We say that there exist two constants, which I'll call c and n naught, so that t of n is no more than c times f of n for all n that exceed or equal n naught. So the role of these two constants is to quantify what we mean by a constant multiple and what we mean by sufficiently large in the English definition. C obviously quantifies the constant multiple of f of n, and n naught is quantifying sufficiently large. That's the threshold beyond which we insist that c times f of n is an upper bound on t of n. So going back to the picture, what are c and n naught? Well, c of course is just going to be 2, and n naught is the crossing point. So if you look at where 2 f of n and t of n cross, and then we drop the asymptote, this would be the relevant value of n naught in this picture. So that's the formal definition. The way to prove that something's big O of f of n, you exhibit these two constants, c and n naught, and it better be the case that for all n at least n naught, c times f of n upper bounds t of n. One way to think about it, if you're trying to establish that something is big O of some function, it's like you're playing a game against an opponent, and you want to prove that this inequality here holds, and your opponent wants to show that it doesn't hold for sufficiently large n. You have to go first. Your job is to pick a strategy in the form of a constant c and a constant n naught, and your opponent is then allowed to pick any number n larger than n naught. So the function is big O of f of n if and only if you have a winning strategy in this game. If you can upfront commit to constants c and n naught so that no matter how big an n your opponent picks, this inequality holds. If you have no winning strategy, then it's not big O of f of n. No matter what c and n naught you choose, your opponent can always flip this inequality by choosing a suitable large value of n. I want to emphasize one last thing, which is that these constants, what do I mean by a constant? I mean they are independent of n. So when you apply this definition and you choose your constant c and n naught, it better be that n does not appear anywhere. So c should just be something like 1,000 or 1,000,000, some constant independent of n. So those are a bunch of ways to think about big O notation in English. You want to have a bound above for sufficiently large numbers n. I've shown you how to translate that into mathematics. I've given you a pictorial representation and also a sort of game theoretic way to think about it. Now let's move on to a video that explores a number of examples. Having slogged through the formal definition of big O notation, I want to quickly turn to a couple of examples. Now, I want to warn you up front, these are pretty basic examples. They're not really going to provide us with any insight that we don't already have, but they serve as a sanity check that the big O notation is doing what its intended purpose is, namely to suppress constant factors and lower order terms. Obviously, these simple examples will also give us some facility with the definition. So the first example is going to be to prove formally the following claim. The claim states that if t of n is some polynomial of degree k, so namely ak n to the k plus all the way up to a1n plus a naught for any integer k, positive integer k, and any coefficients ai's, positive or negative, then t of n is big O of n to the k. So this claim is a mathematical statement. It's something we'll be able to prove. As far as what this claim is saying, it's just saying big O notation really does suppress constant factors and lower order terms. If you have a polynomial, then all you have to worry about is what is the highest power in that polynomial, and that dominates its growth as n goes to infinity. So recall how one goes about showing that one function is big O of another. The whole key is to find this pair of constants c and n naught, where c quantifies the constant multiple of the function you're trying to prove big O of, and n naught quantifies what you mean by for all sufficiently large n. Now, for this proof, to keep things very simple to follow, but admittedly a little mysterious, I'm just going to pull these constants C and N naught out of a hat. So I'm not going to tell you how I derived them, but it'll be easy to check that they work. So let's work with the constants N naught equal to 1. So that's a very simple choice of N naught. And then C we're going to pick to be the sum of the absolute values of the coefficients. So the absolute value of AK plus the absolute value of AK minus 1, and so on. Remember, I didn't assume that the original polynomial had non-negative coefficients. So I claim these constants work in the sense that we'll be able to prove establish the definition of big O notation. What does that mean? Well, we need to show that for all n at least 1, because remember we chose n naught equal to 1, t of n, this polynomial up here, is bounded above by c times n to the k, where c is the way we chose it here, underlined in red. So let's just check why this is true. So for every positive integer n at least 1, what do we need to prove? We need to prove t of n is upper bounded by something else. So we're going to start on the left-hand side with t of n, and now we need a sequence of upper bounds terminating with c times n to the k for our choice of c, underlined in red. So t of n is equal to this polynomial underlined in green. So what happens when we replace each of the coefficients with the absolute value of that coefficient? Well, you take the absolute value of a number, either it stays the same as it was before, or it flips from negative to positive. Now, n here we know is at least 1, so if any coefficient flips from negative to positive, then the overall number only goes up. So if we apply the absolute value to each of the coefficients, we get an only bigger number. So t of n is bounded above by the new polynomial, where the coefficients are the absolute values of those that we had before. So why was that a useful step? Well, now what we can do is we can play the same trick, but with n. So it's sort of annoying how right now we have these different powers of n. It would be much nicer if we just had a common power of n. So let's just replace all of these different n's by n to the k, the biggest power of n that shows up anywhere. So if we replace each of these lower powers of n with the higher power n to the k, that number only goes up. Now the coefficients are all non-negative, so the overall number only goes up. So this is bounded above by the absolute value of ak n to the k, up to absolute value of a1 n to the k plus a naught n to the k. I'm using here that n is at least 1, so higher powers of n are only bigger. And now you'll notice this, by our choice of c, underlined in red, this is exactly equal to c times n to the k. And that's what we had to prove. We had to prove that t of n is at most c times n to the k, given our choice of c for every n at least 1, and we just proved that. So, end of proof. Now there remains the question of how did I know what a workable value of c and n naught were. And if you yourself want to prove that something is big O of something else, usually what you do is you reverse engineer constants that work. So you would go through a proof like this with a generic value of c and n naught, and then you'd say, well, if only I choose c in this way, I can push the proof through. And that tells you what c you should use. If you look at the optional video on further examples of asymptotic notation, you'll see some examples where we derive the constants via this reverse engineering method. But now let's turn to a second example, or really I should say a non-example. So what we're going to prove now is that something is not big O of something else. So I claim that for every k, at least 1, n to the k is not big O of n to the k minus 1. And again, this is something you would certainly hope would be true. If this was false, there'd be something wrong with our definition of big O notation. And so really this is just to get further comfort with the definition, how to prove something is not big O of something else, and to verify that indeed you don't have any collapse of distinct powers of polynomials, which would be a bad thing. So how would we prove that something is not big O of something else? The most frequently useful proof method is going to be by contradiction. So remember, proof by contradiction, you assume what you're trying to establish is actually false, and from that you do a sequence of logical steps culminating in something which is just patently false, which contradicts basic axioms of mathematics or of arithmetic. So suppose in fact n to the k was big O of n to the k minus 1. So that's assuming the opposite of what we're trying to prove. What would that mean? Well, we just refer to the definition of big O notation. If in fact n to the k hypothetically were big O of n to the k minus 1, then by definition there would be two constants, a winning strategy if you like, c and n naught, such that for all sufficiently large n, we have a constant multiple c times n to the k minus 1, upper bounding n to the k. So from this, we need to derive something which is patently false. That will complete the proof. And the easiest way to do that is to cancel n to the k minus 1 from both sides of this inequality. And remember, since n is at least 1 and k is at least 1, it's legitimate to cancel this n to the k minus 1 from both sides. And when we do that, we get the assertion that n is at most some constant c for all n at least n naught. And this now is a patently false statement. It is not the case that all positive integers are bounded above by a constant c. In particular, c plus 1, or the integer right above that, is not bigger than c. So that provides the contradiction. That shows that our original assumption that n to the k is big O of n to the k minus 1 is false, and that proves the claim. N to the k is not big O of n to the k minus 1 for every value of k. So different powers of polynomials do not collapse. They really are distinct with respect to big O notation. In this lecture, we'll continue our formal treatment of asymptotic notation. We've already discussed big O notation, which is by far the most important and ubiquitous concept that's part of asymptotic notation. But for completeness, I do want to tell you about a couple of close relatives of big O, namely omega and theta. If big O is analogous to less than or equal to, then omega and theta are analogous to greater than or equal to and equal to, respectively. But let's treat them a little more precisely. The formal definition of omega notation closely mirrors that of big O notation. We say that one function t of n is big omega of another function f of n if eventually, that is, for sufficiently large n, it's lower bounded by a constant multiple of f of n. And we quantify the ideas of a constant multiple and eventually in exactly the same way as before, namely via explicitly giving two constants c and n naught, such that t of n is bounded below by c times f of n for all sufficiently large n, that is, for all n at least n naught. There's a picture, just like there was for big O notation. Perhaps we have a function t of n, which looks something like this green curve. And then we have another function, f of n, which is above t of n. But then when we multiply f of n by 1/2, we get something that eventually is always below t of n. So in this picture, this is an example where t of n is indeed big omega of f of n. As far as what the constants are, well, the multiple that we use, c, is obviously just 1/2. That's what we're multiplying f of n by. And as before, n naught is the crossing point between the two functions. So n naught is the point after which c times f of n always lies below t of n forevermore. So that's big omega. Theta notation is the equivalent of equals, and so it just means that the function is both big O of f of n and omega of f of n. An equivalent way to think about this is that eventually t of n is sandwiched between two different constant multiples of f of n. I'll write that down and I'll leave it to you to verify that the two notions are equivalent. That is, one implies the other and vice versa. So what do I mean by t of n is eventually sandwiched between two multiples of f of n? Well, I just mean we choose two constants, a small one c1 and a big constant c2, and for all n at least n naught, t of n lies between those two constant multiples. One way that algorithm designers can be quite sloppy is by using O notation instead of theta notation. So that's a common convention, and I will follow that convention often in this class. Let me give you an example. Suppose we have a subroutine which does a linear scan through an array of length n. It looks at each entry in the array and does a constant amount of work with each entry. So the merge subroutine would be more or less an example of a subroutine of that type. So even though the running time of such an algorithm, a subroutine, is patently theta of n, it does constant work for each of n entries, so it's exactly theta of n. We'll often just say that it has running time O of n. We won't bother to make the stronger statement that it's theta of n. The reason we do that is because, as algorithm designers, what we really care about is upper bounds. We want guarantees on how long our algorithms are going to run, so naturally we focus on the upper bounds and not so much on the lower bound side. So don't get confused. Once in a while, there'll be a quantity which is obviously theta of f of n, and I'll just make the weaker statement that it's O of f of n. The next quiz is meant to check your understanding of these three concepts: big O, big omega, and big theta notation. So the final three responses are all correct. And I hope the high-level intuition for y is fairly clear. T of n is definitely a quadratic function. We know that the linear term doesn't matter much as n grows large. So since it has quadratic growth, then the third response should be correct. It's theta of n squared. And it is omega of n. So omega of n is not a very good lower bound on the asymptotic rate of growth of t of n, but it is legitimate. Indeed, as a quadratic growing function, it grows at least as fast as a linear function. So it's omega of n. For the same reason, big O of n cubed, it's not a very good upper bound, but it is a legitimate one. It is correct. The rate of growth of t of n is at most cubic. In fact, it's at most quadratic, but it is indeed at most cubic. Now, if you wanted to prove these three statements formally, you would just exhibit the appropriate constants. So for proving that it's big omega of n, you could take n naught equal to 1 and c equal to 1/2. For the final statement, again, you could take n naught equal to 1 and c equal to, say, 4. And to prove that it's theta of n squared, you could do something similar, just using the two constants combined. So n naught would be 1. You could take c1 to be 1/2 and c2 to be 4. And I'll leave it to you to verify that the formal definitions of big omega, big theta, and big O would be satisfied with these choices of constants. One final piece of asymptotic notation, we're not really going to use this much, but you do see it from time to time, so I wanted to mention it briefly. This is called little o notation, in contrast to big O notation. So while big O notation informally is a less than or equal to type relation, little o is a strictly less than relation. So intuitively it means that one function is growing strictly less quickly than another. So formally, we say that a function t of n is little o of f of n, if and only if for all constants c, there is a constant n naught beyond which t of n is upper bounded by this constant multiple c times f of n. So the difference between this definition and that of big O notation is that to prove that one function is big O of another, we only have to exhibit one measly constant c, such that c times f of n is an upper bound eventually for t of n. By contrast, to prove that something is little o of another function, we have to prove something quite a bit stronger. We have to prove that for every single constant c, no matter how small, for every c there exists some large enough n naught beyond which t of n is bounded above by c times f of n. So for those of you looking for a little more facility with little o notation, I'll leave it as an exercise to prove that, as you'd expect, for all polynomial powers k, in fact, n to the k minus 1 is little o of n to the k. There is an analogous notion of little omega notation expressing that one function grows strictly quicker than another, but that one you don't see very often, and I'm not going to say anything more about it. So let me conclude this video with a quote from an article back from 1976 by my colleague Don Knuth, widely regarded as the grandfather of the formal analysis of algorithms. And it's rare that you can pinpoint why and where some kind of notation became universally adopted in the field. But in the case of asymptotic notation, indeed, it's very clear where it came from. The notation was not invented by algorithm designers or computer scientists. It's been in use in number theory since the 19th century, but it was Don Knuth in '76 that proposed that this become the standard language for discussing rate of growth, and in particular for the running time of algorithms. So in particular, he says in this article, on the basis of the issues discussed here, I propose that members of SIGACT, this is the special interest group of the ACM, which is concerned with theoretical computer science, in particular the analysis of algorithms. So I propose that the members of SIGACT and editors in computer science and mathematics journals adopt the O, omega, and theta notations as defined above, unless a better alternative can be found reasonably soon. So clearly a better alternative was not found, and ever since that time this has been the standard way of discussing the rate of growth of running times of algorithms, and that's what we'll be using here. This video is for those of you who want some additional practice with asymptotic notation, and we're going to go through 3 additional optional examples. Let's start with the first one. So the point of this first example is to show how to formally prove that one function is big O of another. So the function that I want to work with is 2 raised to the n plus 10. Okay, so it's the 2 to the n function that you're all familiar with, but I'm going to shift it by 10. And the claim is that this function is big O of 2 to the n, so without the 10. So how would one prove such a claim? Well, let's go back to the definition of what it means for one function to be big O of another. What we have to prove is we need to show that there exist 2 constants such that for all sufficiently large n, meaning n bigger than n naught, our left-hand side, so the function 2 to the n plus 10, is bounded above by the constant multiple c times the function on the right-hand side, 2 to the n. Right? So for all sufficiently large n, the function is bounded above by a constant multiple of 2 to the n. So unlike the first basic example where I just pulled the 2 constants out of a hat, let's actually start the proof and see how you'd reverse engineer the suitable choice of these 2 constants. So what a proof would look like, it would start with 2 to the n plus 10 on the left-hand side, and then there'd be a chain of inequalities terminating in the c times 2 to the n. So let's just go ahead and start such a proof and see what we might do. So if we start with 2 to the n plus 10 on the left-hand side, what would our first step look like? Well, this 10 is really annoying, so it makes sense to separate it out. So you could write 2 to the n plus 10 as the product of two terms, 2 to the 10 and then the 2 to the n, also known as just 1024 times 2 to the n. And now we're looking in really good shape. So if you look at where we are so far and where we want to get to, it seems like we should be choosing our constant c to be 1024. So if we choose c to be 1024, and we don't have to be clever with n naught, we can just set that equal to 1, then indeed star holds, so the desired inequality. And remember, to prove that one function is big O of another, all you got to do is come up with one pair of constants that works. And we've just reverse engineered it, just choosing the constant c to be 1024 and not to be 1 works. So this proves that 2 to the n plus 10 is big O of 2 to the n. Next, let's turn to another non-example, of a function which is not big O of another. And so this will look superficially similar to the previous one. Instead of adding 10 in the exponent of the function 2 to the n, I'm going to multiply by 10 in the exponent. And the claim is if you multiply by 10 in the exponent, then this is not the same asymptotically as 2 to the n. So once again, usually the way you prove that one thing is not big O of another is by contradiction. So we're going to assume the contrary, that 2 to the 10n is in fact big O of 2 to the n. What would it mean if that were true? Well, by the definition of big O notation, that would mean there are constants c and n naught, so that for all large n, 2 to the 10n is bounded above by c times 2 to the n. So to complete the proof, what we have to do is go from this assumption and derive something which is obviously false, but that's easy to do just by canceling this 2 to the n term from both sides. So if we divide both sides by 2 to the n, which is a positive number since n is positive, what we find would be a logical consequence of our assumption would be that 2 raised to the 9n is bounded above by some fixed constant c for all n at least n naught. But this inequality, of course, is certainly false. The right-hand side is some fixed constant independent of n. The left-hand side is going to infinity as n grows large, so there's no way that this inequality holds for arbitrarily large n. So that concludes the proof by contradiction. This means our assumption was not the case, and indeed it is not the case that 2 to the 10n is big O of 2 to the n. So our third and final example is a little bit more complicated than the first two. It'll give us some practice using theta notation. Recall that while big O is analogous to saying one function is less than or equal to another, theta notation is in the spirit of saying one function is equal asymptotically to another. So here's going to be the formal claim we're going to prove. For every pair of functions, f and g, both of these functions are defined on the positive integers, the claim is that it doesn't matter, up to a constant factors, whether we take the pointwise maximum of the two functions or whether we take the pointwise sum of the two functions. So let me make sure it's clear that you know what I mean by the pointwise maximum, by max f and g. So if we look at the two functions, both functions of n, maybe we have f being this green function here, and we have g equal to this red function. Then by the pointwise maximum, max fg, I just mean the upper envelope of these two functions. So that's going to be this blue function. So let's now turn to the proof of this claim, that the pointwise maximum of two functions is theta of the sum of the two functions. So let's recall what theta means formally. What it means is that the function on the left can be sandwiched between constant multiples of the function on the right. So we need to exhibit both the usual and not, but also two constants, a small one c1 and a big one c2, so that the pointwise maximum of f and g, whatever they may be, is wedged in between c1 and c2 times f of n plus g of n, respectively. So to see where these constants c1 and cn are going to come from, let's observe the following inequalities. So no matter what n is, any positive integer n, we have the following. Suppose we take the larger of f of n and g of n. And remember, now we've fixed the value of n is just some integer, like 23. And now f of n and g of n are themselves just numbers, maybe they're 57 and 74 or whatever. And if you take the larger of f of n and g of n, that's certainly no more than the sum of f of n plus g of n. Now I'm using in this inequality that f and g are positive, and that's something I've been assuming throughout the course so far. Here I want to be explicit about it. We're assuming that f and g cannot output negative numbers. Whatever integer you feed in, you get out something positive. Now the functions we care about are things like the running time of algorithms, so there's really no reason for us to pollute our thinking with negative numbers. So we're just going to always be assuming in this class positive numbers, and I'm actually using it here. The right-hand side as the sum of two things is bigger than just either one of the constituent summands. Secondly, if we double the larger of f of n and g of n, well then that's going to exceed the sum of f of n plus g of n. Right? Because on the right-hand side we have a big number plus a small number, and on the left-hand side we have two copies of the big number. So that's going to be something larger. Now it's going to be convenient, it's going to be more obvious what's going on if I divide both of these sides by 2, so that the maximum of f of n and g of n is at least half of f of n plus g of n. That is, it's at least half of the average. And now we're pretty much home free. Right? So what does this say? This says that for every possible n, the maximum is wedged between suitable multiples of the sum. So 1/2 f of n plus g of n is a lower bound on the maximum. This is just the second inequality that we derived. And by the first inequality, that's bounded above by once times the sum. And this holds no matter what n is, any n at least 1. And this is exactly what it means to prove that one function is theta of another. We've shown that for all n, not just for n sufficiently large, but in fact for all n, the pointwise maximum of f and g is wedged between suitable constant multiples of their sum. And again, just to be explicit, the certifying choices of constants are n naught equals 1, the smaller constant is 1/2, and the bigger constant equals 1. And that completes the proof.